Question 1 is a good example of a have you done your revision or not kind of question, because there's no thinking involved here. You just either know this or you don't. The answer is A, tetramethylsilane, which is this. And the point about it is that although it's got 12 hydrogens in it and 4 carbons, all 12 of those hydrogens are equivalent, because all 4 methyl groups are equivalent, and therefore all 4 carbons are also equivalent to one another. So you only get 1 carbon peak and you only get 1 proton peak, and in both cases they're defined as being at 0 ppm, so that's the chemical shift reference. Question 2, you have to choose between these 4 and decide which one is a secondary amide. So what you should know is that an amide group is CON something, and there will be 2 other things attached there. And what distinguishes primary, secondary, tertiary amides is the usual thing of what's attached to the nitrogen. So a primary one would have 2 hydrogens there, so CONH2 is a primary amide. A secondary one will have 1 carbon and 1 hydrogen attached there, and a tertiary one will have 2 carbons attached there. So we're looking for a secondary one, which means that it's got to have that group in it. And so going through, you can see this one doesn't fit the bill. It's got a carbonyl group and a secondary nitrogen with just 2 carbons attached to it, but they're not next to each other. Okay, the carbonyl group and the nitrogen have to be attached for it to be an amide group. So it's not that one, and it's not that one for the same reason, because again the carbonyl group and the nitrogen are not directly attached, so you've got to learn what the actual functional group is. So that narrows it down to these 2, and you can see that this is the one that fits the bill, because that nitrogen is attached to 2 carbons, so it's like that, that's a secondary amide. This one is a tertiary one, because the nitrogen is attached to 3 carbons, so C is the answer for that one. Question 3 requires us to decide which one of these 4 does not react with nucleophiles. So a sensible place to start would probably be to remind yourself what nucleophiles do, because you only know 2 kinds of nucleophilic reaction. The first is where you have C delta plus attached to something like a halogen. Okay, so it could be Cl or Br, or indeed OH or Cn as well, but something that will pull electrons away from the carbon, and it goes, like that. So that's nucleophilic substitution. So anything that can do that would react with a nucleophile, so that rules that one out, because that's a haloalkane, so it can do that. The other type of reaction is nucleophilic addition, which, remember, is where you have a carbonyl group, and then your nucleophile attacks like that to start an addition reaction. So that's a property of aldehydes and ketones that you should know. So we've got nucleophilic substitution would take out the haloalkanes, nucleophilic addition would take out aldehydes and ketones. So we've got an aldehyde there, we've got a ketone there, so that leaves that one. That looks a bit weird written like that as a structural formula, but if you write that up properly you realise CH2 means there must be a double bond there. So what you've actually got is there's the CH, and then you've got CH2. So it's an alkene. And of course what alkenes react with is electrophiles, not nucleophiles. So B is the right answer. Question 4 is a reminder about this classification of organic compounds that you need to be confident about. So at the first level there's this simple division in that if the compound contains a benzene ring, it's called aromatic. If it has no benzene ring, then it's called aliphatic. Okay, so you need to know those 2 words, and as far as we're concerned at A level it means simply that. Aromatic means it contains a benzene ring, aliphatic means it doesn't contain a benzene ring. It's actually a bit more complicated than that, but that's what it is as far as A level is concerned. Now within the aliphatic ones, if it contains some kind of ring that isn't a benzene ring, then it's called alicyclic, and if it has no ring, then it's not alicyclic. Okay, so these are just subsets. An alicyclic compound is aliphatic because it's a subset of the aliphatic ones, but if an aliphatic compound doesn't contain any kind of ring, then it's just aliphatic. Turning to these particular compounds, they're none of them drawn with the aromatic ring drawn in that conventional way, but hopefully everyone's happy with the idea that if you have 3 double bonds drawn like that in a ring, then in reality those delocalize together to make an aromatic ring. So that one is aromatic. In fact, both those rings are aromatic, but you can particularly clearly see that that one is. That one is, because you have the 3 double bonds there, and that one is drawn as such, but that one isn't, because you only have 2 double bonds in the ring. So it's not aromatic, it's therefore aliphatic, but it does have a ring in it, and it's therefore alicyclic. So that one is the answer, is C. Question 5 wants to know which of these is not planar. And the thing is that rather than necessarily have to go through and work out what shape each one of them is, you can just scan down straight away and see which one leaps out at you as not being planar. And hopefully you'll spot straight away that this is ethane. So ethane is that. And of course you know that when you have a carbon with 4 bonds around it like that, it's tetrahedral. So it's going to look like that, and the other one will be the same, like that. So it's clearly not planar, because if it's tetrahedral, it means these bonds that we've drawn as wedged are coming out of the plane, these ones that we've drawn with dashes are moving behind the plane. So that one is clearly the answer, is B. Just for completeness, we'll just run through the other ones. This is ethene, which is an alkene, and of course remember that the thing about alkenes is that in order to get that sideways overlap of the p orbitals to make the pi bond, the whole thing has to be planar. So that one is H2CO. You would normally write like this is methanal, and the same reason as that one, that in order to get the sideways overlap of the p orbitals, that whole thing has to be planar. HCN, if you only have 3 atoms, then by definition they're all in the same plane. You can't have any 3 things other than being in the same plane. In fact, HCN is linear, because you just have 2 regions of electron density repelling each other. But of course linear is a subset of being planar. So B is the answer. You didn't really need to go through all those other shapes. Question 6 wants to know the number of proton NMR peaks in that compound. It's not very friendly drawn out like that, and the issue that's going to be of importance here is their symmetry, meaning that the number of peaks might be fewer than you would expect. And if you can't see that instantly, the thing to do is just draw it out. So you can see we've got 1, 2, 3, 4, 5 carbons. Ordinarily I would do a skeletal formula, but because we're talking about proton NMR, it helps to see the carbons and the hydrogen, sorry, the hydrogens especially, obviously, because they're the ones. So if you just draw it out like that, we can just go through and say, right, the end ones, that's the COOH, so that's that carbon dealt with, and we've got a COOH at this end as well, so that's that carbon dealt with. Then we've got a CH2 there, and likewise we've got a CH2 here, and now you can see the symmetry emerging, and then here we've got CHOH. So that's the structure. And once you've drawn it out like that, it's very easy to answer the question, because you can see that that hydrogen and that one are equivalent because of the symmetry running down the middle there, so they'll just give 1 peak. Likewise, that CH2 and that CH2, they are equivalent, so they'll just give 1 peak between them, so that's 2 peaks. And then this carbon in the middle has no symmetry partner because it's the middle one, but it has 2 different types of hydrogens attached to it, that one and the OH one. So you have 1, 2, 3, 4 peaks in the spectrum, and therefore the answer is B. Atom economy, you will recall, is the percentage of the mass of the product which is taken up by the product you're interested in. So the higher the atom economy, the less waste mass there is. So you can, without actually calculating the numbers, realise that with each of these you've got the product you want, which is the ethanol, and then in all but this case there's something else as well. And you can see the bigger the mass of the bigger the MR of the other stuff relative to the ethanol, the lower the atom economy will be, because more of the mass is being taken up by the other stuff. Now the one you've got to be careful of is this one, because of the 2's in the equation. One way to think about it is, well, we could rewrite this equation as a half of that goes to one of those and one of those. That's just a legitimate way of writing the same equation. That makes it easier to get your head around it, because then you're just comparing 1 mole of ethanol in each case, and these are the waste products. So CO2, if you add it up, has an MR of 44. This one has no waste product, so the MR is 0 for the waste product, because there isn't one. Hydrogen bromide adds up to 80.9. and ethanoic acid adds up to 60.0. So if you look at those, you can see hydrogen bromide is the one that has the biggest MR for the waste product, and therefore that will be the biggest percentage of the total MR on the right, so that has the lowest atom economy, because ethanol is contributing the smallest percentage of the total, so therefore C is the answer. You didn't need to actually calculate the numbers. That would obviously given you the right answer, but it would have taken a lot more time. So just by thinking it through, you can realise that the one that has the biggest MR of the waste products is going to contribute the most to the percentage, and therefore is going to take the atom economy down the most. So C is the answer. Question 8 is asking us about the destruction of ozone catalysed by NO. The easiest way to do this one, almost certainly, is just to treat it as a recall question, because you are meant to have memorised this mechanism in advance. So you therefore could hopefully very quickly write down the mechanism, which is this, that the propagation phase is that O3 reacts with NO. NO has a lone pair on the nitrogen, and remember, it just grabs an oxygen atom out of the O3 to give you O2 plus NO2, and NO2 still has a lone pair on the an unpaired electron on the nitrogen. And the second part of that propagation cycle is that the NO2 then goes on and reacts, and this is the bit you have to remember, that it reacts this time with an oxygen atom, which you have lots of in the upper atmosphere, because UV is breaking down oxygen and ozone all the time. So you can react with one of those, and it just grabs one of those oxygens out of there to give you your NO back and form another O2. So the overall reaction is O3 plus O goes to 2O2, because the NO is destroyed in this step but recreated in that one. So if you've memorised that in advance, you can just quickly scribble it down if it helps you to remember it, and then just go through and match it to one of those, and you can see that you had to go all the way down the list to D. That's the one that appears on the list, because that's the second step. All these other ones look vaguely plausible, but they're not what happens. So you needed to have learnt that one, really. Question 9, we have to match this spectrum to the compound it came from. So remember, with infrared spectra, that you're basically not interested in that half of the spectrum. That's the fingerprint region, which is very important for forensic purposes, matching to a specific compound, but no good for working out functional groups. So we're just looking at what we've got here. The one around 3000 is CH, so that's no use, because all these compounds obviously have CH in them. So the ones that we're interested in is this is an OH peak. You can see 3200 to 3600, and it's specifically an alcohol OH peak, so we're looking for a compound that has an alcohol OH group in it. And this is one that you don't see so often, but that you've got to be on the lookout for, is a nitrile peak. You can see that in your data sheet. It's listed between, what does it say, 2220 to 2260, so it's a very sharp, narrow peak, as you can see there, and that's what that one is. So we're looking for a compound that has both of those. The other thing that's worth noticing is that there is no carbonyl peak, because the carbonyl peak would be about here, and there isn't one. So we can straight away rule those two out, because they both have carbonyl peaks, so it can't be either of those. There's got to be one or other of these. They both have the OH peak, but only this one has the nitrile peak. So that one is the answer, which is B. As I say, you don't see that so often, obviously, as you've done many more examples with OHs and carbonyl groups, so make sure you're on the lookout for that one. The other one, which you haven't seen so often, is actually one that comes in quite a similar place to the carbonyl peak, and that's an alkene peak. And again, you can see that in your data sheet. it's listed around 1620 to 1680, so again a very sharp peak, and it comes sort of about here, so quite close to where a carbonyl peak would be, but much narrower. If you've got a carbonyl peak, sometimes you can't even see that because it can get hidden underneath it, but if there isn't one there, then be on the lookout for that, because C double bond C is also something that could come up and that you might easily miss, but obviously there wasn't one here. So just those 2 points to B as your answer. Question 10 wants to know what reagent is needed to turn benzene into this compound. Whenever you add some kind of carbon chain onto a benzene ring, you hopefully recognise that as a Friedel-Crafts reaction, which is the standard way of extending a carbon chain by sticking an aromatic ring onto it. And the simple way to figure out what you need is always to remember that wherever the benzene ring ends up in your product will have been a chlorine in the reagent, and so you just rewrite the thing, same before, but wherever the benzene ring is, you just put the chlorine there instead, and that's the reagent you need, which means that the answer is C for that one. Remember, you need also an aluminium chloride catalyst, but the reagent is that, which is the acyl chloride, which is C.